So we will today look at our last example. So we will do one more example on longitudinal analysis. And this is an example that I have taken from the Heck et al. Book. Let me share my presentation. Okay, so yes, this PPT has been uploaded. Right, this is the example that we are going to talk about today. Now, if you remember, our first example that we had done was about uh, uh, testing math achievement for a student, and the student was nested in schools. Now we want to check whether student math achievement has the change has taken over time. Is there a change in student math achievement over time? So what is the trend? That is the first thing that we want to check, whether this is going to be a linear trend, whether it is going to be a quadratic trend, etc. Right? Then we say, what is the shape of the developmental change uh, for people? Okay, whether it is linear or whether it is more complex, quadratic, etc. And are there differences in development between groups of individuals, right? So what are the individual level predictors that are going to be there? Okay, so the data is from Heck et al., the book, chapter number 5. And there are 8,670 students who have been tested across three time occasions. There is a school identifier. These 8,670 students have been nested under 515 schools. Okay, so they are in these schools. Okay, and there is individual identifier 1 to 46. Index, it is telling us 1, 2, 3, which is essentially saying first time, second time, third time. That is how the data is. And then time is essentially coded 0, 1, 2, based on index. It has been coded 0, 1, 2, and there is a square of time, quad time 0, 1, 4. So square of time becomes quad time 0, 1, 4. Then there is orth time, okay, orthogonal coding like we had done yesterday. Okay, time has been coded as orth time. So it is -1, 0, and 1. And orth quad, so basically the square has been coded as orth quad 1, -2, and 1. And then there are these test scores varying from 24.35 to 99.99. And then there are two individual level predictors, effective, whether, so the students were asked whether their teacher is effective in teaching maths. And it is a dichotomous variable. 0 is not effective, 1 is effective. And SES, which is basically measuring Z score of the socioeconomic status, right, or socioeconomic status within school. So it is Z score of the student, socioeconomic status of the student, and it has been standardized. Okay, and then these are they have just shown you can try with other non-linear codings. Okay, I'm not going to go into that. They have tried out different codings for time. So you code 0.51, 0.61, 0.7.53, and so on. Okay, but that is not needed. We can just work with 0.12, 0.14 as the square of time, and then we do the orthogonal coding. So let us start with, for a change in this example, let us start with our SPSS. Okay, so let us do SPSS. So I have the SPSS data opened. This is my SPSS data file that I have given to all of you in the longitudinal folder. I am looking at the horizontal SPSS ch5 underscore h dot sab, right? So let me close this file, growth data, and we are left with now SPSS CH5. So ID, and I have pruned it, okay, because I want to show you how to prepare the file. Remember, step 0, I was telling you, is data preparation, right? This is what we have to do. Step 0, preparing the data file and coding the time variable. So when you will be collecting data, this is how you will be collecting it. You are saying ID1, okay, this is within school 1, and the maths achievement has been taken at 3 time points: 49.66, 50.09, 54.72, and this is the effectiveness score, whether the student believes teacher is effective or not. 0 means not effective, 1 means effective, and this is the socioeconomic status score. So effective and SES are basically between individual predictors, between subject predictor, and test 1, test 2, test 3 are within subject. They are being taken from the same individual ID and then nested under this school. So this is the horizontal data, assuming we don't have the time variable, we don't have the time square variable, we don't have the orth time, we don't have the orth square. So what is it that we will do? Remember, the first thing that we did was restructure. So we go to data and then we do restructure. So it says, what do you want to do? We want to convert horizontal into vertical. I go to next. Then how many variable groups do you want to restructure? There is only one variable group, test 1, test 2, test 3, right? So we say 1 and then next. Case group identifier. So I say use selected variable, which is ID in this case, because ID is continuous 1 to whatever numbers. And then test 1, test 2, test 3 are the variables to be transposed. And I give it a name, test. This is the maths test score. What are the fixed variables? Effective and SES. These are fixed. They just have to be copied. Okay. It says you can choose variables to copy to new file as fixed variables. And then next. How many index variables do you want to create? I want to create one. Next, and I give it a name. So it says it will number it sequentially, index values 1 to 3. So I say index, give it the name index. And then I say next. Drop variables, handling of variables not selected. I say keep and treat as fixed variable. So SCH code, for example, keep it as fixed variable. And then I say next. And what do you say? It says, do you want to restructure the data now or paste? I say paste the syntax and finish. Right? So a syntax file has opened. So I say now restructuring the school data from horizontal to vertical format. Okay, and then I do vars to cases, right? I run this and you will see the data has been restructured. So you see ID, SCH code, effective, SES, index has been created, and test scores now have been changed from horizontal to vertical format. Do not save it because otherwise it will overwrite the horizontal file. So we should always say save as. And I will give it a name, SPSS, SPSS CH5V. Let me just, so that we don't overwrite, we say V underscore 1, so that it does not overwrite the data set that I have given you. Now we have to create a time variable. So I say transform compute variable, and I say time is equal to index minus 1, right? This will become my time variable, and I go to syntax and I say creating time variable. I run this, and you see a time variable has been created. Then what do we say? We say time square, which is equal to time multiplied with time. And I paste the syntax and I get this syntax. I say creating time square variable, and I run this. Okay, so you see time square has come 0, 1, 4, 0, 1, 4, and so on. Now what do we have to do? We have to create auth time and auth time square variable. So we say transform data, no, sorry, data, and you would see, I think transform. So it says recode into different variables. So what is the variable? Time. And what should be the name? We say auth time. Auth time. Output variable is auth time, just like we had done last time. Then we say what is the value? 0 is to be coded as, let me just remember, -101. So -1, and 1 has to be coded as 0, and 2 has to be coded as 1. And I say continue, and I say paste the syntax. I say now I call this as creating auth time variable, and I get my auth time. Now what do we say? We have to code this, remove this, and we have to create time square. So we say auth time square. Okay, what are the values? Let us remove all of these. So let me, this is 1 minus 2, 1. So 0 has to be coded as 1. This has to be coded as -2, and 4 has to be coded as 1. 1 minus 2, 1. And I say continue, and I paste the syntax. So now this comes,
So,
yes.
so just a curious question here.
Hmm.
What if you wouldn't have pasted and just done okay? The output have come automatically only, no?
Yes,
Is there
absolutely.
any is there any specific reason why you prefer doing the coding besides teaching us, of course?
You tell me now, after doing all these sessions, if you were doing this analysis,
Yes, sir.
will you remember 1 month later what buttons you were clicking?
Got it. Okay. Got it. Okay.
What buttons you were clicking 1 month earlier to get the output that
Hmm.
you are getting?
Right.
If
Okay.
you don't save these commands, how will you know? How will you replicate the output that you got, say, 6 months earlier? You did
Right.
the analysis of your thesis, you started you moved on to some other project and you submitted a paper for publication. And
Yes, sir.
let's
Yeah,
say
yeah,
the
no, I get that.
reviewer says, can you reproduce the analysis?
Right, right. That's fine, sir. So this one, anyways, even if we click OK, then also this will come, no? What we can see here, right?
The
In the
this
dialog box there, in the
this
commands,
the
instead of,
syntax, right?
yes,
Here,
sir, this one. Yes,
yes,
sir.
but then you will still have to paste it in a syntax file. How will you save it?
Okay. Okay, sir. Okay,
How will
sir.
you
Got it.
save this? Either you save the output file,
Hmm.
but
Okay.
output file will become so clumsy because you would have run so many analysis that
Right.
the commands you would find in between.
Right. Got it. I usually save the output file, but I see what you're uh,
Yeah, so
teaching. Yeah. Got it.
I
Right.
always save all, and it is not just because I'm teaching all of you, but I
Yes, sir.
always save my syntax so that I don't have to worry later on what commands I was running 1 year before.
Got it, sir. Thank you for this. Yeah. Right. That's a good practice. I'll follow. Thank you.
Yes, so now we have auth time. And the beauty of syntax is, Kanika, you can write as many comments as you want. So
Right.
that you
Okay, sir.
remember what is it that this command is actually doing,
Right, sir. Got it.
which is not possible in a output file.
Sure, sir. Right. Thank you.
Okay, so we have created our auth time square variable. Now we can say our data is ready for analysis. It is now ready and they are all numeric in nature, which is fine. And this is now done. So our first step, or you can say step zero, is which was actually preparing the data file for analysis is now ready. Let us now move on to again doing, maybe we can say step zero, which is, or step one, which is to run the null model, right? So subject is ID and repeated is time. And for the time being, we will do scaled identity. Till the time we actually start examining the L1 error structures, we will keep scaled identity as the default, and then when we come to exploring L1 structure we will change L1 structure, which is repeated covariance time, and I say continue. Then what is the dependent variable? The dependent variable is test. Now this is the test, this is the output variable. It is a null model, so there are no explanatory variables. In the fixed, you have only intercept. So we have said include intercept, continue. In the random, we will say include intercept and it varies per combinations, right? We say continue. Estimation, we will say maximum likelihood and we say continue. Statistics, I always prefer parameters and covariances of random and residuals. Continue. EM means nothing to do, save, nothing to do, okay, and then you do paste. And now we will write, we can say, let us call it as, instead of step 1 let us use the name run 1 and we say estimating the null model. And now I run this command. Okay, so we have got this output. You see number of parameters is 3, right? And then so I will again open my SPSS runs file that we had created yesterday. I have uploaded this also. Let me save this as another name. Let us call this as math SPSS runs, math school SPSS runs. Okay, let me delete all of this. Okay, remove all the colors. So my format is ready now. I don't have to make all these commands, all these columns and all this again. So let us go to our output and let us look at our null model. AIC is 193.893.757. BIC 193.918.256. Okay, deviance is 193.887.757. DF is 3. Okay, right. This is our fit, and this is the intercept. Okay, fixed effect. This is gamma 00. It is highly significant. This is the overall mean. And you have your repeated measures. Sigma square R is 78 and intercept is sigma square U0 is 30.49. So what is going to be our ICC1? It is 30.498. Okay, I will keep it to 3 decimal places, divided by 30.498 plus 78.101. Right, this is our ICC, and I will copy this and paste. Okay, so for both these I will left center them and I will put an equal to, and I get my ICC. That means what? We can say 28% variance in the maths performance of students can be explained by individual level or L2 variables, L2 effects, right? That is 28% variance is attributed to. Let me also open the book so that we can also tally what we are doing. Okay, if you have the book with you, you can look at chapter number 5. Let us go to chapter, this is chapter 4 of the book and chapter 5. Okay, so they have done the plotting. I have not done it. I have directly come to, okay, let us do model with no predictors. This is page number 190. Okay, this is y ti is equal to pi 0 I. These are the equations, right? This is what we have. They are using epsilon. I had written the equation of r ti. Then pi 0 I is equal to beta 0 0 plus u 0 I. So your null model equation becomes y ti is equal to beta 0 0 plus u 0 I plus epsilon ti. Okay, so they have done this. Let us come to the output. Okay, and this is the output, 78.101 and intercept is 30.505. So they would have computed, yeah, here it is. As a rough estimate, we can calculate the proportion of variance in math achievement that is between individual as about 0.281 or 28.1%. And what have we got? We have got 0.281 as well. So we are saying that 28.1% variance is can be associated with individual level variation, right? This is what we have also concluded. Now we are saying what is the shape of the trajectory. This is the next question, right? So what is it that we do? We go to what is the shape of the trajectory. So in our mixed model, we go to continue, okay, and we first introduce the time variable. So we want to test this equation, beta 0 0 beta 0 time ti. Okay, let me write the equation so that it becomes easy for all of us to follow. So what is it that we are saying now? We are saying shape of trajectory, right? So what are we saying? We will say test ti is equal to, we will first introduce pi 0 I plus pi 1 I time ti plus r, and pi 0 I am going to write beta 0 0 plus u 0 j, and pi 1 I for the time being I am going to write as a constant. So my equation becomes test ti is equal to beta 0 0 plus beta 1 0 time ti plus u0 j, u0 not j, u0 I plus r ti. So we will have two fixed effects, the intercept and the time. And you will have one random effect associated with intercept, one random effect associated with, this is modeling linear trend. Linear trend. Then what we are going to do? We are going to model quadratic trend. So we will say test ti is equal to pi 0 I plus pi 1 I time ti plus pi 2 I time square ti plus r ti. Then again I am going to say pi 0 I is equal to beta 0 0 u0 I by 1 I beta 1 0 by 2 I is equal to beta 2 0. When you combine this equation, you get test ti is equal to beta 0 0 beta 1 0 time ti beta 2 0 time square ti plus u0 I plus r ti. Now this will have three fixed effects and you will continue to have two random effects. This is, we are saying, testing quadratic trend, right? So we will first check, should there be or is there a linear trend or a quadratic term? Should we limit ourselves to time variable or should we also bring in time square variable, right? So this is the first step, testing the shape of trajectory. This is what I am going to do now. Okay, now I go to my SPSS and I say time. So the first variable is time, and I say I want to test along with the intercept, I want to test the effect of time. Okay, the fixed effect associated with time. Continue. Random effect, it is still intercept, So I will press continue. Everything else is the same. So I will paste this command. And what am I writing now? I will say this is our run to estimating the, or you can say examining the linear trend in math scores. Okay, and now I run this. So it has run. Now let us record. I have said random intercept only, linear time trend. What is our AIC? It has become 189.381.422. BIC is 189.414.087. What is our deviance? 189.373.422. What is the DF? It is 4. Number of parameters you see is 4 here. So what is our delta deviance? It is 193,887 minus 189,373. What is our delta DF? It is 4 minus 3. And is this significant? How do we test it? We say chi-square distribution right-tailed. This, comma, the, let me just expand this a little bit so that the complete formula comes. So we say chi-square distribution, this, comma, this. Okay, so we see it is p less than 0.001. Okay, it is highly significant. The delta deviance is highly significant. And which is a better model? With a linear time trend is a better model. Okay, now we go to analyzing our quadratic trend. Okay, so this is same. Now, because we will bring in time and time square, instead of time and time square, we will bring in orth time and orth time square. And our fixed effects are going to be orth time and orth time. And now, because we have two variables, so we will say main effects. We want to check their main effects. Continue. Random, it is still only random intercept, so we continue. Everything else is the same, so I say paste, and I go to my syntax file and I say run 3 examining the quadratic trend in math scores. Okay, and I run this command. Okay, it has run. There is no error. So let us record our model fit. Quadratic time trend, random intercept only. It has become 189,377.705 is our AIC. 189,418.536 is our BIC. Deviance is 189,367.705 is our deviance. Our DF is 5. You see number of parameters here is 5. So what is our delta deviance compared to the previous model? It is 18973 minus this. Okay, and what is the delta DF? It is 5 minus 4. And is this significant? It is significant at p less than 0.05. Let us look at the coefficients, the fixed effects, estimates of fixed effects. Intercept is significant, orth time is significant, and orth time square is also significant, and it is negative. So basically it is a parabola and an inverted parabola. So you have a inverted U-shaped profile because the time square is significant and it is negative, right? So and it is significant at p less than 0.05. So what is the time trend that we are now going to stay with? We are going to say that there is not just a linear time trend, there is also a quadratic time trend, right? And it is also giving us a better fit. Okay, so this is what we have concluded now. Now comes the next step, which is, let me go to my whiteboard. So what have we concluded now? We are saying that our data has actually a quadratic trend. Now the next step is, for this quadratic trend, so we have concluded that there is a quadratic trend. So essentially our equation is test Ti is equal to pi 0 I plus pi 1 I time Ti plus pi 2 I time square Ti plus r Ti. Now I am going to check whether there is random intercept as well as random slope. So what do I say? Pi 0 I is equal to some beta 0 0 plus u 0 I. Then I say pi 1 I is equal to beta 1 0 plus u 1 I, and pi 2 I will for the time being hold it at a constant. Then what I will do is I will also replace this 2I with beta 20 plus u 2I. So here what will be our equation? We will get our equation as test Ti is equal to beta 00 plus beta 10 time Ti plus beta 20 times square Ti plus u0 I plus u1 I multiplied with time Ti plus r Ti. What will be our equation here? It will become test Ti is equal to beta 00 plus beta 10 time Ti plus beta 20 times square Ti plus u0 I u1 I multiplied with time Ti plus u2 I multiplied with time square Ti plus r Ti. Okay, so we are testing whether there is random slope associated with time. Here we are testing random slope associated with time square, right? That is what I'm going to do now. That is the run here. So we go to our data and we say analyze mixed models, linear, continue. Now we know there is orth time and orth time square. So there is no change in the fixed effects. First change is I will now add Along with intercept, I am saying there is random auth time also. And I am going to keep this level 2 structure as unstructured, right? Remember what is level 2 structure, which is yesterday we were talking about. We said, and we have also discussed this when we were doing MLM models. We said L2 structures is, in this case you will have sigma square u0, sigma square u1, and you will have sigma u0 u1. This is unstructured. And I said you can also have, this is un, unstructured. And we can also test diagonal, where we will say you will have sigma square u0, sigma square u1, and diagonal says the diagonal elements are significant, others are all zero, right? So I'm keeping it as unstructured because this is most realistic, right? There is no assumption associated in unstructured level 2. That is what my run here is. I have changed the random covariance type to unstructured, and I have brought in auth time. And I say continue, estimation, statistics, EM mean, everything is the same. So I'm going to paste this in my syntax, and I'm going to say this is run 3, examining random slope associated with our time variable. Okay, and we are saying L2 structure is equal to UL, unstructured. Correct. So now we run this, and it has run without giving us any error. So this is a good news, or there is no convergence issue. So I have set linear time trend. Okay, let us now change this. It is not linear, it is quadratic. Quadratic time trend, random intercept and random slope associated with time. And I have written L1 is scalar identity, L2 is UN. What is our AIC? It is 189.284.495. What is our BIC? It is 189.341.658. What is the deviance? 189.270.495. Our DF is 7. You have number of parameters 7. So let us check, is it better or worse? So this minus 189.270, this is delta deviance. What is our delta DF? 7 minus 5. Is this significant? Let us check this. This is highly significant. So modeling random slope associated with time is useful. Now let us go to our next, where we will also say random slope associated with time square or quadratic variable. So I say continue, fixed, no change. So I will press continue, random. I will now say also bring in auth time square, right? This is the there is random intercept, random slope associated with auth time. There is random slope associated with auth time square as well. Continue, okay, and I paste it. And what is the thing? I say run 4. It is examining random slope associated with time and time square variable. L2 is still unstructured. Let us see if SPSS will be able to estimate this. And it has given us a warning. It says there are convergence issues. I have not been able to estimate this unstructured. Right? What will now be the unstructured? What is the unstructured for time, time square, and intercept? What will the unstructured matrix look like? It will look like sigma square u0, sigma square u1, sigma square u2. Then you will have sigma u0 u1, sigma u0 u2, sigma u1 u2, sigma u1 u2, sorry, u1 u2. So how many unique? 1 2 3 4 5 6, right? So it has to now estimate these six values, and that is why it has SPSS gives us a convergence six unique values. Let me write it, unique values. So SPSS says, well, I have convergence problem here. It is too much to ask. You see intercept, orth time, and time square, and that is why you see here it has said unstructured. There are six values, six parameters that I need to calculate, that you are asking me to compute. Let us write it nonetheless, and we will put a star, and we will tell ourselves that this failed, right? Time and time square. Okay, so our AIC now is 189.121.724. BIC is 189.203.387. Deviance is 189.101.724, and our DF is 10 because there are 10 parameters to be computed. Let us check our, but let me also put a star here, right, which says it is, it has not estimated, it has not converged. What is the delta deviance? This minus this. What is our delta df? It is 10 minus 3. Okay, 10 minus 7, which is 3. And is this significant? It is significant, but let us write star means convergence not achieved. Okay, this is what star means for us. Convergence not achieved. So what am I going to do? I am going to check if we change this to, if at the L2 level we change this to diagonal, will this work? Right? Rather than saying unstructured, I am going to uh, put some assumption, add some constraint. I am saying that estimate only the diagonal values, assume all the covariances are 0. I continue, and then I paste, and in my syntax I write run 5. Everything else is the same. I say L2 structure is diagonal, and I run this. Let us see. So this also is facing issues. Diagonal is also facing issues. Let us try with random. If I just say variance components, though this is also diagonal only, let me not paste the command as of now. This is also actually diagonal. By default, it is diagonal. So it is okay. So we are seeing that it is giving us an error, and they make a mention of this in their book also. Okay, vary across group, and you see, yeah, defining the slope, and so we can estimate. We emphasize there is no one way to proceed in developing initial growth model. We generally favor latter approach. Okay, and we now test both beta 20 and plus u. Okay, then we need to keep in mind that we are limited in number of random effects by the number of repeated measures. Okay, yeah. If we if we do try to estimate the quadratic effect also, we receive the warning message in figure 5.7 regarding the model's failure to converge onto a solution. With the quadratic component fixed, though the substitution of equation 5.10 through the substitution of 5.10, 5.14 and 12 into, we arrive at a single equation. Equation 5.16 suggests that intercept and linear component time are randomly varying across because the quadratic component is merely defining the shape of growth within individuals. This suggests building the explanatory model for student growth rate on randomly varying linear components. So what have they have done? They have said that we are not going to model randomness in the quadratic term. We will go back to just having u1 time ti rather than bringing in u2 time square ti term also, because we are getting convergence issues. Okay, so this is what they are doing. Doing they are just doing random intercept unstructured for intercept and time. Okay, so we can say that, well, because this ran into convergence issues, let us mark it in maybe orange color. So what we are going to do is we are going to stick with, and we also tried out diagonal. Diagonal also gave us an issue. Okay, so we will, let us control Z here, insert. We can say we tried diagonal also, and diagonal also gave issues. So we are going to keep only random intercept and random slope associated with time, and we will keep L1 and scalar. Okay, so we let us go to our SPSS output. For record, let us record their AIC BIC 189.333.817. This is for diagonal. 189.390.981. Deviance is 189 319.817. The parameters are 7 delta deviance. You can see unstructured was better, so we say this is equal to this minus this minus this, and what is our delta df? This minus this, and it is significant. But we are saying that unstructured is better in model fit than diagonal. Okay. However, both of them have convergence issues. So we are going to retain this as the model, right? This is retained. Let us put a remark here. Okay. And make a thick outside border. We say this is retained. Right. Now we go to, therefore, let us start with this. Okay. So with this retained, what is the next thing? We are now going to, what is the next set of iterations that we will do? So what is it that we have finalized now? Retained in SPSS, because of all the convergence issues, we are saying quadratic trend, random intercept, and random slope for time only. Right? This is what we have retained now. This is now, what is the step? We will test different L1 structures. We know our L2 structure is unstructured. Now we are going to test our L1 structures also. So we go to our model, we go to SPSS, mixed models. Now what is it that we are going to do? This is scaled. So first let me remove, okay, I have made a mistake. I cannot go back. So I will go first to linear. Now instead of scaled, let us try our AR1, right? This is what we had said, auto-regressive 1. So we continue, and then for random fixed, there is going to be no change. In random, we are going to remove this, and we will keep only time, and L2, we will make it as unstructured. Continue. Okay, so now I will paste the syntax, and now what am I going to do? I'm going to say, I will copy this command, this comment. I'm saying run 6, examining random slope, not examining. So we will say quadratic trend, random slope, intercept, and random slope associated with time variable. L2 structure is UN, L1 structure is equal to AR1. Now let us run this command and see what does our software do. Okay, now you see even with AR1 it gives a warning, it gives a problem, and they have also documented this. Okay, with time. Now you see in I have also put this table in my presentation actually. Okay, yes. This table is from the book Heck et al. They say auto-regressive AR1. This also does not work. This gives an error. Model did not converge. They have put a star here. So AR1 also SPSS is unable to estimate it, and that is what we are also getting. We are seeing this output and it is giving us convergence issues. Let us record it nonetheless. Okay, we say L1 is AR1 and this is also having convergence issues. Okay, let me record the fit anyways. So I say 189.276.203, 189.341.532, then deviance 189.260.203, and df is 8. What is delta deviance? It is, if we compare it with the random slope, this one model, because this is the one that is retained, and this one, it is going to be 10. And what is df? It is this minus this is delta df. And if I copy this formula here, it is significant at p less than 0.01. However, we have a convergence problem here as well. Okay, so that means AR1 is not going to work for us. We try out something else. So let us see if AR1 is not working. Will ARH1 work with heterogeneous AR1 as well as heterogeneous? So continue, random is the same, and I paste. Let me just ascertain that ARH1 is also failing, and I replace this with ARH1. Let me run this now. It is running. I think I have asked too much from SPSS. It is still running. All right, so we have convergence issues. It has given up. Let me copy this, paste it here, and I say AR H1. It is also failing to converge. What is the AIC? It is 189.121.782. BIC is 189.203.445. Our deviance is 189.101.782. And if I compare this, sorry, the DF is 10. Let me compute the DF, delta deviance, sorry. It will be this, and delta DF is 10 minus 7. And this is also significant, but it is failing to converge, so we may need to try something else. So let us see what they have tried. They are saying identity unstructured. We have tried this. They are saying diagonal and unstructured. Okay, let us try diagonal as L1 and unstructured as L2. Let us go and do this now. We say mixed models, and instead of ARH1 we say diagonal. Okay, continue. Random is the same, nothing is to be changed, so I paste this syntax and I now say run number 8. Quadratic trend, random intercept and random slope associated with time. L2 structure is unstructured, L1 structure is diagonal. And I run this. All right, so good news is that this a, it has been able to estimate without any convergence issues. This is a good news for us. So we change this to L1 is diagonal. Let us record the AIC 189.119.724. What is BIC? It is 189.193.220. Deviance is 189.101.724. Our DF is 9. So what is delta deviance? It is this model minus this. What is delta DF? It is 9 minus 7, our previous retained model. And so this is highly significant. So let us remove the star here because it has been able to estimate. Okay, let us highlight this also in yellow color. That means this, they were all failing to converge. Okay, so diagonal is still better. It has assumption, right? What are the L1 structures we talked about? We said, okay, we have done scaled identity, diagonal we have tested, AR1 we have tested, ARH1 we have tested. Okay, they are all failing. Unstructured, if these are failing, there is no chance unstructured will run. What is only left is let us try out compound symmetry, okay, as our L1 structure. So I go to my data and I say analyze mixed model, and instead of diagonal you will see there is compound symmetry as well. Compound symmetry. Okay, let us keep the simplest compound symmetry model. Everything else is going to be the same, nothing to change. Random is still unstructured, and we paste this command. Okay, and I will say this is run number 9 now. And this is L1 structured compound symmetry. Then I run this model. Let us see. Okay, so again convergence issues. So compound symmetry has also failed. This also has convergence. Sorry, why did I edit this? This should be diagonal. The next try is CS, and this has convergence issues. Let us record the AIC anyways. So 286.495.189.351.824. Okay, deviance is 189.270.495. Parameters is 8. What is the delta deviance? The deviance anyways has increased as compared to our diagonal. So the delta deviance is actually this much, and delta df is this. It is significant. So our diagonal matrix is anyways better. So let me give this a coding again. Let me give this green coding, and I say this model is also retained. This is our next step. Okay, so what have we now established? That there is quadratic trend, random intercept and random slope associated with time, and L1 structure diagonal and L2 structure unstructured is giving us the best fit for for all of the models that we have seen. This is a model that is able to estimate properly, okay, and it has the lowest deviance, right? So our last step now is, what is it that we have so far understood? That our quadratic trend, random intercept, random slope for time, okay, and we are saying our L1 structure is diagonal, our L2 structure is unstructured, this has no convergence issues, and this has least deviance, or we can say best fit. Now comes the last thing, which is to bring in our L2 predictors, right? The last aspect of our estimation is to, with quadratic trend, add L2 predictors, right? So what is it that we are going to say? Our test Ti is equal to pi 0 I plus pi 1 I time Ti plus pi 2 I time square Ti plus R Ti. Now we are going to say pi 0 I is equal to beta 0 0 plus beta 0 1 SES I plus beta 0 2. In our case, there are two L2 predictors, effectiveness of the math teacher and SES plus U0 I. Then we have pi 1I beta 10 plus beta 11 SESI plus beta 12 effective I plus U1I and pi 2I is equal to beta 20 beta 21 SESI beta 22 effective I plus U2I. Now this would have been the ideal situation. However, you remember that we have got convergence issue when we tried to model random slope for time square variable also. So in this case, we are not going to write this, rather we are going to say this will be held at a constant. In ideal situation, I should have also checked if this randomness in pi 2I could also be explained by individual predictor, but this did not run for us, right? When we looked at our runs, we said quadratic time trend, random intercept and random slope associated with time and time square. And this ran into problems. SPSS was unable to estimate this. So we said we will hold this at a constant pi 2I, we will hold it at a constant. And that is what they are also talking about. Let us look at adding. So they say adding between subject predictors, right? And what are the equations they write? They say pi 0I is equal to beta 00 plus beta 01 SESI beta 02 effective I plus U0I. And they say pi 1I is equal to beta 10 beta 11 SESI beta 12 effective I plus U1I. And beta 20 is being held at a constant. Correct? There is no U2I term. And that is what we are going to get. Let me derive the final equation. So if we hold this at a constant, what is the equation we are going to get? We are going to get test Ti is equal to beta 00 plus beta 01 SESI plus beta 02 effective I plus beta 10 time Ti plus beta 20 time Ti multiplied with SESI plus beta, what have I written? Why it is not beta 20, it is beta 11 and beta 12 time Ti multiplied with effective I plus U0I plus U1I multiplied with time Ti plus Rti. And there is going to be one more term which is equal to beta 20 times square Ti. Right? This term beta 20 multiplied with time square Ti. This is the equation that is this is the final equation that is written here in the book. YTI is equal to beta 00, beta 01 SESI, beta 02 effective I, beta 10 orth time, beta 11 SES into orth time, beta 12 effective into orth time, beta 20 orth quad, U1 orth time, U0, and there is a typo here, it should be plus, they have missed the plus here. Okay, so this is what we are going to do now. So how will we do it? We will go to analyze and mixed model linear. So we will go back to keeping L1 structure as diagonal. Continue. Now we are going to bring in effective and SES also as our covariates. In the fixed effects, we are going to bring in the main effects of SES and effective, and then I am going to bring in effective and orth time interaction, add and orth time and SES interaction, which is orth time into SES. So we have orth time square, effective, SES, orth time into effective, orth time into SES. And I say continue. Then random, nothing is to change. This will be the same. And now I paste my syntax. It says this is the final, and I say run 10, which is going to be quadratic trend, random intercept and random slope associated with time, L2 structure, UN, L1 structure, diagonal, and then I say adding L2 predictors, SES, comma, effective to random intercept and random to explain and random associated with time. Okay, so this is our run. Let us now see if this runs. So the good news is there are no convergence issues. Okay, and let us record the, so let me do this. Let me remove the color and I say L2 predictors SES comma effective added to explain random intercept random slope associated with what is our fit. Let us record that. AIC is 186825.956. What is our BIC? It is 186.932.118. What is our deviance? It is 186.799.956. What is our DF? It is 13. Number of parameters are 13. Okay, so what is delta deviance? We check it with the last retained model, which is 189101 minus this. What is the delta df? Is 13 minus 9, Is this significant? It is highly significant. Let me remove the color. Okay, and this has been able to estimate. Okay, and so this is our next retained model, right? This is our next retained model. Okay, and let's give it the color. Okay, let us now look at the estimates of our fixed effects. Intercept is significant, orth time is significant, orth time square is significant, effective is significant, SES is not significant, but we see that the interaction with effective and the interaction with SES is both significant. So you have significant interactions with effective and you have significant interaction with SES also. Let us look at the results that are given in the book. Okay, 13, and you see orth time into SES is significant and it is negative, and orth time into effective is also significant and it is positive. That means they are more. So if a student believes that the teacher is effective, then the change with time is even more, right, of the maths performance. If the socioeconomic status is high, we are seeing a slight reduction actually in the rate of growth of the student, right? That is what we are seeing in terms of their maths performance. So we see regarding variables that may explain variability in math growth rates between individuals, we can see that the linear interaction is significant at p less than 0.05. This coefficient can be interpreted as higher SES levels demonstrate slightly less growth. This is what I just said, that the growth is less compared to students with at the grand mean. The test for students' perception of teacher effectiveness is also significant. This suggests that students with teacher they perceived as effective have a higher growth rate over time compared to their peers who perceive their teachers to be average or below in effectiveness. The quadratic polynomial is also significant, which implies that student growth rate slows slightly over time. This is what I said, because the coefficient is negative, we say it is a downward parabola or an inverted U shape. In this model, we did not propose any cross-level interaction related to explaining the slowing of math growth rates, because we did not model, the SPSS cannot model or failed to converge when we had brought in the time square varying also, right? So this becomes our final, you can say, estimates, and we can paste this table in our SPSS file, and I will show you how to do the plot. If you have these estimates, okay, we can then create a plot also for, and we can say this is a model that is, now let me expand this. This is model that is giving us the least deviance. Okay, so this I am going to highlight now. This is our final retained model. Okay, and this gives us the least deviance, and we have modeled our L1 and L2 structures. Okay, Any questions anybody has on this? And we will plot it. So they have given a plot also later on. So they have, you can report it like this: intercept. This is a good table. You can report it. Model 1, when you had only intercept and quadratic time, then you brought in SES and effective, then this is the interaction. Okay, and then you have this is how you would report. And yeah, this is with orth time and orth quadratic and orth time and orth quadratic into. Okay, they have in this table actually they are showing the effects of they have multiplied orth quadratic into effectiveness. I think this is a typo again. This should be orth time into effective. That is what we received. We saw they have tried with orth quadratic into SES, orth quadratic into effective also. But then this gives us convergence issues. Okay, and let us do that actually. See if we can bring in the interaction between orth time square into effective and orth time square into SES. Okay, though I am not modeling the randomness, but I am still actually it doesn't make sense what they have done, but let me just write this in the syntax. I say run 11 L2 predictors to explain random slope associated with time square. Run this. Okay, so it has added these effects, which is, and let me write this also here. And I say associated with time. So this is AIC is 186744 dot 935. BIC is 186867.429, and then 186714.935, and our DF is how many parameters? 15. So what is delta deviance? It is this minus this. Delta df is equal to this minus this. And is this significant? This is also significant. Okay, though I still have my concerns on why would we add this when we had not modeled randomness associated with orth time square. Okay, but in case, and yeah, this is the result that they are reporting. I think if I just compare this, Let me close this. And so 79 intercept is 49.741. Then orth time is 2.409. Orth time square is minus 414, and it is significant. SES is not significant. Effectiveness is 5.820. It is significant. Then orth time into SES, it is minus 0.152. Then orth time into effectiveness, it is 3.322. This is a typo. Okay, this should be orth time. And then orth quadratic into if SES is minus 0.006. It is not significant. And orth quadratic into effective, it is 0.605. And this is your AIC that they have reported. So the AIC is smallest in model number 5. So you can say that orth, SES and effectiveness are moderating both orth time, and effectiveness is moderating even the orth time square relationship. Okay, and then what they have done is they have plotted this with respect to effectiveness. So you see there is a downward parabola. This is a upward parabola. So effectiveness is actually moderating the relationship between maths and we will see, we will plot this as well after we take a break. We will come back and run this on R, and then we will also plot it. Okay. Usually, usually you will, yeah, I'm just wondering why would I include uh, this quadratic multiplied with SCS and quadratic multiplied with time square multiplied with SCS and time square multiplied with effectiveness if I had not modeled the randomness associated with time square. Okay, so yeah, I have just produced, but this to me is still something that I'm not very confident of because this was, we had not modeled randomness associated with time square. However, this is how we would do the run. This is your final, you can say, model fit table. Any questions anybody has around this, what we have done? Okay, so let us take a break. It is about 4:41. Let's take a break. Let's come back at uh, let's come back at 5. Maybe take a 20-minute break. Let's come back at 5 and we'll do the last analysis using R. Yeah.
Sir, today also we'll go up till 7.
No, I think we should be able to stop by 6:30. Just that
Okay, sir.
our run is remaining, so we should be able to finish by 6:15, 6:30.
Okay, sir.
Yeah.
Thank you.